Good afternoon, you all. My name is Funda Yavuz, and I will be presenting this presentation today on behalf of Dr. Upul. So here is the outline that I'm going to follow today. Well, bridges are important components for non-motorized and motorized traffic, and the health of bridge system assures the integrity of transportation network. However, there are 600,000 bridges in the United States, and 25% of them are deficient or functionally obsolete, so they require rehabilitation or total replacement. Well, accelerated bridge construction methods are implemented over conventional constructions to reduce the mobility impact time, because conventional construction of bridges takes a long time, and we close the road length and it just really impacts the transportation. So accelerated bridge construction assures that the motorized and non-motorized traffic is allowed in the construction zone while the bridge is constructed nearby. So FHVA developed time metrics for accelerated bridge construction. It has different methods. So it starts from 1 to 24 hours to up to 3 months. So it has 3 different methods that we can classify. First one is the prefabricated bridge elements. So the bridge elements are fabricated in the fabrication process, and they are brought to the site and they're implemented. So even it's still in months, it is less than the conventional construction mobility impact time. And then we have self-propelled modular systems. It's even less in the mobility impact time. So it has weeks, and we actually we use the self-propelled systems to put the bridge in place. And we have slide-in bridge construction having the mobility impact time of days. And well, it actually reduces the mobility impact time with a special system called sliding. So the new bridge is constructed near the existing bridge while the traffic is allowed during that construction time. So only in days the traffic is closed in that road link, and the new bridge is slid in place after the existing bridge's demolition. So traditionally, the user cost from this reduced mobility impact time is used to justify the additional cost of accelerated bridge constructions. However, there are a lot of inconveniences that this bridge construction brings to its surroundings and communities. Therefore, they should be considered in the decision-making process of bridge alternatives. So our objective is to develop a decision-making model to quantify the economic impact on surrounding communities and businesses from a bridge construction project. And the methodology we followed is here. Like we reviewed the literature and developed the model, and then we applied that model to a case study and we drew conclusions out of it. So the cost groups that we used in this study is user cost, environmental cost, and business revenue change, and we could classify those costs into 2 basic titles, having economic impact on surrounding communities and economic impact on surrounding businesses. So the major differentiation in here is the direct impact on the flow of dollars. So communities doesn't have the impact on flow of dollars while the other one has. And I will start talking about user cost from passenger vehicles, and I will not really go into the details of calculations, so that it is nothing really fancy. Here the driver delay cost, vehicle operating cost, and accident cost is calculated over here. And then additionally, we calculated passenger delay cost and passenger accident cost while the traffic is traveling in the work zone. So that's basically during the construction time. And then we have the detour time, which is really shorten with the accelerated bridge construction, but we need to quantify the work zone time and the detour time at the same time. We're adding the passenger delay cost and passenger accident cost here as well. So with that being said, I can step into the environmental cost right now, and it consists of air pollution, water pollution, and climate change. So the pollutants considered in the air pollution are on the board, and then their quantification are carried with considering work zone and detour as well. So the summation of this healthcare costs from passenger vehicles and trucks are again on the board. And then we have actually the other costs related to air pollution. The previous one was healthcare costs, and now we are considering the reduced visibility, agricultural damage, and property damage, as well as forestry damage. So they can be quantified as a percentage of the total healthcare cost from trucks and passenger vehicles. And then another pollution type is water pollution. So the reduced speed limits doesn't have anything to do with water pollution. So the only part we quantified this water pollution is the detour, while the traffic is traveling through detour. So we have passenger vehicles and then trucks as well. The total water pollution damage is the summation of those two. And then we quantified the climate change, again, considering the gases, the global warming potentials of greenhouse gases. And then this is actually the same quantification method with the healthcare cost quantification, but since the derivation processes of the unit cost is different, so we had to do it separately. So that concludes the economic impact on surrounding communities part. Now I'm going to step into the economic impact on surrounding businesses part. So this is again the user cost, but from trucks now. So we don't have the passenger. Here we only have the driver delay cost, vehicle operating cost, and accident cost for businesses. And then this is for detour. The previous one was for work zone. And then we have the business revenue change, because the bridge construction disrupts the traffic flow, therefore the customer flow to the surrounding businesses. So this is actually like a back engineering. Instead of using the business data, we are trying to use the household data, how much they spend on a specific business, because it is so hard to obtain the business revenue data. It's not even possible using it with tax data, because this is a pretty short time. It's not in years, it's just in months, and it's so hard to observe the change. So that is why we're making back engineering and try to calculate in terms of houses and their expenditure. That is why we're using average expenditure per household here, and the households, the number of households without direct access during that mobility impact time while the bridge is, the road link is closed. So for this business revenue change calculation, it depends on the complexity of road network on which you're focusing on. So for large urban areas, traffic demand models can be employed, but for rural areas with simple networks, the simple hand calculation is enough, hand analysis is enough. So if this model needs to be further developed, further generated, these are the possible questions that could be asked after the construction is completed. So with that being said, I'm going to step into the case study in Potterville, Michigan. So the agency decided to go for a slide-in bridge construction having the least mobility impact time of accelerated bridge construction, since there is a residential area up north and then school district in the south of the bridge. So the bridge construction site is over there. No? Oh. Okay. So that is why they wanted to go for a slide-in bridge construction. So here is the actually the construction time. So they construct a new bridge near the existing bridge, so they keep the traffic flowing. And then for 2 days, they closed the road link and they demolished the existing bridge and slid the new bridge into its permanent place. So that is why the mobility impact time here is 2 days of a weekend, and then the reduced speed limit duration is 237 days for slide-in bridge construction over here. So for comparison purposes, we considered 180 days mobility impact time of conventional construction, and we investigated the effects, but could it have been done if the bridge was delivered with conventional construction. So that is why we have the comparison columns over here with SIBC and conventional construction. Here is the site-specific data from the bridge location, and then we have the work zone length of 0.5 mile. So we have the detour route for passenger vehicles in the middle, and then we have the detour route for trucks. And then here is the user cost parameters and associated databases that are utilized in the quantification method. And then here is the user cost with SIBC and conventional construction. So the most significant criteria here is the mobility impact time and the duration of reduced speed limit. And then the detour length, of course, well, in terms of bridge construction. And then we have the databases and associated cost parameters for environmental cost. So with SIBC and conventional construction, and then the environmental cost here is on the board right now. So as you can see, the difference is pretty huge with conventional construction and SIBC. And then when we come to the economic impact on surrounding businesses, this is calculated with trucks. So here is the data and associated parameters again. And then here is the result of that computation. So it's almost 5 times more with conventional construction than SIBC. So when we come to the business revenue change, like I said, this is a very new and challenging process and like a backwards engineering. So we had to determine the influence area, which is basically the commercial center of Potterville, and then the city limits are anticipated generating this map. So in order to find the number of households without direct access, so we had to draw the shortest lines to the nearest commercial centers to Potterville, and then we unified their midpoints here on the second picture. And then on the third picture, we identified the pieces that will be out of access during that mobility impact time, since we have the bridge in the middle, bridge construction in the middle. And then the fourth picture is developed using the nearest roads. So when we combine those two maps together, so we have the influence area at the bottom, and we have the area without direct access. So when we count the households in that area is 250. So these are actually the shops which are in the Potterville business area, the commercial area. That is why we considered those shops, the restaurant, gas station, pharmacy, liquor store, and auto repair shop. And then we have the visits, and the demographics now tool is utilized to be able to carry out these computations. So as a result, the difference is pretty huge, again here with the business revenue change. So when we sum those up with SIBC and conventional construction in terms of economic impact on surrounding communities, it is almost 5 million. With conventional construction, it's 700,000 with accelerated bridge construction, which is sliding bridge construction. And then when we think about the economic impact on surrounding businesses, the difference is even larger. So it's around 800,000 with conventional construction and 50,000 with SIBC. So as you could see here at the bottom of the table, we could say that SIBC is more favorable than conventional construction when we think about economic impact. So we tried to simplify, at least try to find some ways to simplify this procedure and try to see the contribution percentages of each cost categories here. So, and then we deducted that environmental costs can be eliminated in quantification from the quantification model with the rural networks. However, when this model is applied to a more complex urban areas, so it's not really wise to say to eliminate environmental costs from the economic impact on surrounding communities. However, when it comes to economic impact on surrounding businesses, this should be businesses, sorry about it, both of the contributing cost parameters should be kept in the economic impact analysis procedure. So this model was developed as a decision-making tool for the use of highway agencies, which can be applied to any sort of actually highway project. So if this model is wanted to be applied as a post-construction analysis tool, so the site-specific data should be collected during the construction, before the construction, and after the construction, as well as the speeds of the passenger vehicles and trucks. So like I said, this is again valid. Travel demand models can be applied in here, but it again depends on the complexity of road network. So more accurate values of percent influence area access limitations and then the frequency of customers can be found through surveys, and that surveys could be upgraded to a automated surveys utilizing now modern mobile devices. So as a result of this study, aggregate unit daily cost for economic impact can be deducted. However, a large sample of sites should be achieved to say something about aggregate unit daily cost. So thank you so much.